Hello, Algebra 2 students. Hope you're doing well today. We're in rational functions in this chapter, and today's lesson is going to be about different types of asymptotes and holes that can result in our rational functions. So just as a reminder, what a rational number is, which relates to our rational function idea, that is the ratio. So the quick definition, it's the ratio of two integers. So that means then, taking that a step further, that a rational function, that's actually the ratio of two functions. And so an inverse variation, the one we spent the last two lessons on, is an example of a rational function. Remember, that's that if we did functional notation, we'd say f of x equals 1 over x. 1 is a rational function. It could be y equals 1, and y equals x is also a rational function. And so we have to be worried now about the denominator in these rational functions. They can't be equal to 0. So if p of x is some polynomial in the numerator and q of x is some polynomial in the denominator, we have that restriction that anything that makes that polynomial in the denominator 0 must be restricted. That restriction then creates what's called a point of discontinuity. In other words, the curve doesn't go smoothly through that point. There's either an asymptote there or there is a hole there. And I'll go through both variations on that. So the first example and questions relate to finding points of discontinuity. So that's kind of the first part. The second part is then figuring out, is that point of discontinuity going to be an asymptote vertically, or is it going to be a hole? All right, so here's the first function here, y equals, so we got a 3 on the top and then an x squared minus x minus 12. And so to find our points of discontinuity, we're going to have to factor this. And so if we do that factoring, we still have the 3 on top, but now we're thinking what times what makes 12? That then is going to add to a negative 1, and if you figure that out quickly, you should have gotten an x minus 4 and an x plus 3 for the factoring of that denominator. That tells me that my two values of x that make these two different binomials 0, those will be points of discontinuity. In other words, what zeroes it out? What would we have to restrict in this fraction? And 4 and negative 3 are the two values. Oop, that's a positive 4, sorry, and negative 3. So those would be points of discontinuity. And then after we go through a couple more of these examples, we can talk about, is that going to be a vertical asymptote? Is it going to be a hole? What's happening graphically with these? All right, here's so that was part A. Here's another one for you. Give this one a try. Y equals 1 over x squared minus 36. So now I've got a binomial down there. I'll give you just a second, see if you can remember how to factor the difference of two squares. Hopefully you came up with still the 1 on top, but now an x minus 6 and an x plus 6 in whichever order. So those are the two values, 6 and negative 6, that are points of discontinuity. third example, y equals x plus 5 all over 2x squared plus 7x minus 15. So you could guess and check your way to this, but I just wanted to put one on here to do Berry method for a little review. So if we're going to do our factoring of this one, let me move this up a little bit, then the Berry method says, all right, I'll take that 2x, the 2, the coefficient, and the x term, and I'll put 2 of them in. Even though I know I'm putting an extra 2 in, that'll come out later. And then I do the a times the c, so 2 times the 15, I get 30. So now I'm thinking about, all right, factors of 30 that could end up being 7. Since it's subtracting here, I know there's one of each sign. And then 1 and 30, does that work? No. 2 and 15, nope, that's 13 apart. 3 and 10 though, those are 7 apart. And so now I want to make it more positive because it's positive 7x for my middle term, so I'm going to put a plus 10 there and then a minus 3 here. That gives me my factoring now. I can take out this extra 2, which then gives me an x plus 5 when I do that. So the factoring for this is still have that x plus 5 on the top. Then we have a 2x minus 3 in the bottom and another x plus 5. Even though these x plus 5s will end up canceling each other out, it's still a point of discontinuity. So x equals negative 5. That would zero out this second binomial down here. And then what times 2 would make a 3, so that when I subtract 3 I get 0. In other words, I'm just doing this little 0 property on this, saying, all right, how could I get that equal to 0? I would add 3 to both sides, and we get a 2x equals 3, and then divide away the 2. So my other point of discontinuity is x equals 3/2. When you have the top and bottom have a similar factoring or a similar binomial that could get crossed out, that actually forms a hole in the graph. If you just have the point of discontinuity downstairs in the denominator, then that's going to form a vertical asymptote. And I'll give you good notes on this, but that's where we're headed with these. The last example of these would be this. Y equals 2x over a 3x squared plus 4. And if we try and make this 3x squared plus 4 equal to 0, it's not going to give us a regular number. It's going to give us a complex or imaginary number, because we're going to have to end up square root 4/3. So this gives me x squared equals negative 4/3. I don't have to worry about any values of x that would make this 0. So in this case, there are no points of discontinuity for this one. And the reason is we'd be getting x equals the square root plus or minus of negative 4/3. And then we'd have to do some rationalizing on that. The 2 could come out of the square root, but then it'd be a root 3 over 3 with a plus or minus. So those would be the values that could actually make this 0, but they're imaginary. I forgot the I there. Whoops. All right. So the next part, I've got some written out notes for you. Let's get those down so you can see this. Whoops. That comes second. Here's the first one. All right. So like we talked about, points of discontinuity, that's a value of x, and it has to be real, can't be imaginary, that makes the denominator 0. And then vertical asymptotes, like I mentioned quickly, that's when they're just in the denominator. So any 0 that's in the denominator, any point of discontinuity, that's in the denominator that's not in the numerator, that forms a vertical asymptote. And then if we have the same binomial, top and bottom, so the same zero, top and bottom, that's when it forms a whole. And then there is one exception when we end up having two in the denominator of the same type of binomial and one. And I'll go through that example because it is a little bit confusing, but there is one exception to the whole thing. All right, so let's just work through a couple of examples of these. All right, so this would be, for example, 2 problems. Let me move this up just a little bit. And let's say we were given it factored, so we can save ourselves a little time here. X minus 7 all over x plus 1 and an x plus 5. Now you'll notice that I didn't put the top binomial in parentheses. The fraction bar pretty much acts like parentheses, so if you put them there, that's fine. If you left them off, that's also okay. It is just a binomial in the top. There are no repeats, so top and bottom, they're different. So the 0 in the top, that doesn't tell me anything about asymptotes and wholes. It's only the ones in the bottom. So in this case, they're both vertical asymptotes. So vertical asymptotes for this one would be x equals -1. Remember, that would be a vertical line. And also x equals -5. Now I've said and or it's both. Okay, that's the first one. Here's the second one. So what if we had instead y equals x minus or plus 2 on top all over x plus 2 times an x plus 1. Okay, this would have a whole at x equals -2, because top and bottom has the same 0 value, -2 with 0, both of these, so that gives me a whole. And then also there will be a vertical asymptote at this -1 value. All right, third example. How about this one? Y equals x times an x plus 3 in the top. Whoops, sorry. And I've got a x plus 3 in the bottom. So I know you guys didn't see that, but I don't want to redo this whole video here. So there is the x plus 2 and x plus 2 in the top and bottom. That forms a whole at that 0. This x plus 1, that's just going to be a vertical axis. All right, and this third example here, what do you think? Is it going to be a whole, vertical asymptote? Neither. And so there's an x plus top and bottom, that makes a whole at x equals -3. And now, I guess I did this out of order a little bit. I guess it's 2D that we're going to clarify. So this is when we have a whole, we think it's a whole, but it's actually a vertical asymptote because there's 3 of those zeros, 2 in the bottom and 1 in the top. So it would be something like this. What if we had x minus 6 and an x plus 9 on the top, and then 2 x plus 9s and an x minus 6. So I'll do the x minus 6 first. There's 1 in the top, 1 in the bottom. That makes it be a whole. So there's a whole at that x equals 6 value for that 0. Now normally x plus 9 over x plus 9, that would be a whole, but then they put an extra 1 downstairs, so it's kind of like the whole gets crossed out and we're left with just 1 down there now. gives us a vertical asymptote, and that is the exception. So it's not always a hole if it's top and bottom zeros. It's got to be the same number of top and bottom zeros to make that work. And that would be at x equals negative 9. We'll zeros that out. So there's the exception. 2 on the bottom, 1 on the top of the same binomial. That ends up being a vertical asymptote. All right, last little bit is horizontal asymptotes. Let me move this down here. So good news about horizontal asymptotes, at most there's one. So they're either one or none. So I talk about a rational function being binary. That means that the degree of the denominator is more than the degree of the numerator. In that last example, it was bottom heavy because it was degree 3. There were 3 binomials down there and only 2 in the top. When that happens, the x-axis is always a horizontal asymptote. So bottom heavy, if the degrees are more in the denominator, so that's a higher degree than the numerator, then y equals 0 is the one horizontal asymptote for that curve or graph. Top heavy, just the opposite, so the degree of the numerator is more than the denominator, so there's more binomials up top than there is downstairs, then there isn't horizontal asymptote. And then the weirdest one, I think, is when equal degrees. So let's say both were quadratics, top and bottom. Then you would take the lead coefficient of both of them, the top one, the numerator's lead coefficient, divided by the bottom denominator's lead coefficient, gives you the value of the horizontal asymptote. So that a lot of times is a fraction, depending on whether a and b are multiples of one another. And I've got several examples of this to go through as well, and then we'll be done. All right. So let me move this up now. You can pause and copy these down. Probably be good notes to have for this lesson. Here we go. So this would be find the horizontal asymptote or state that it doesn't have one. This would be, for example, 3 problems. So what if we had y equals negative 4x plus 3 on the top and a 2x plus 1 on the bottom? And so now I see there's a point of discontinuity at negative 1/2, but right now we're just focusing on horizontal asymptotes. And yes, it would have a vertical asymptote at negative 1/2. No holes in this one. This is where the degrees are tied. They're both linear binomials. So power 1, that makes this a degree 1 binomial. Power 1 on that, x downstairs as well. That's another linear binomial. So when that's the case, the degrees are equal for each of the polynomials, top and bottom. Then we just take the lead coefficients. So this horizontal asymptote is going to be equal to negative 4/2, which simplifies to just a negative 2. So that's where the horizontal asymptote would be for this graph. Go ahead and check it out on your graphing calculator. Super fast to do. When you type rational functions in your graphing calculator, make sure you put parentheses around the top and the bottom. And sometimes if the bottom has several sets of parentheses, you got to do nested parentheses to make sure that it's dividing that whole polynomial, not just parts of it. So that's a warning. All right, that was the first one. Here's the next one. What if it was y equals x plus 2 on the top and an x squared minus 4x plus 4 on the bottom? This one now, I could figure out that I've got a vertical asymptote down there. This does factor into x minus 2, the quantity squared, so positive 2 would be vertical asymptote, x equals positive 2. We're not doing that for this problem. We're just figuring out horizontal asymptotes for these problems. This is bottom heavy. It's degree 1 on the top, degree 2 on the bottom. So that means we've got y equals 0. for our horizontal asymptote. And then the third example, let's say I had an x cubed on top and an x squared plus 1 on the bottom, and that would be no horizontal asymptotes. It's top heavy. So top heavy, there aren't any horizontal asymptotes. There are a few graph questions. At the end, I'm not going to go over graphing. You've got your graphing calculator. Just make sure that you put in holes, vertical asymptotes. Whoops, move that up. Sorry. Vertical and horizontal asymptotes should be labeled. With equations. So please don't forget that. Very easy to forget writing out the equations for these. We find them and then we forget to put them on the graph. So don't be that kid. All right. And then the assignment here, obviously this is 9.3, and we're on pages 495 to 6, and we'll just do 2 through 34 even. All right, have a good day and do everything your parents say.